Yes, thank you. Okay, let's start with this. So, this is a document, it is not a presentation. So, this document is about Walecka model and advanced RMF approaches in dense matter physics. So, I will be talking more, like I will be writing wherever I feel I should write. Okay. So, I told you so far we are interested in what business? We are interested in equation of state business. We wanted to explore the area of neutron stars. We wanted to explore the area of neutron star like maybe around 3-4 saturation densities or more than that. So, we are interested in the range from 0 to 8 times nuclear saturation density. And if you remember, I told you about, okay, I have the plot right here. Yeah, if you remember, we are mainly focused into this regimes. So, our internship revolves over neutron stars. Okay. So, I want to explore this area, and in this area I can rely on chiral effective field theory. Low energy physics, nuclear physics is experiment thing. So, the theory is chiral effective field theory and some model, some equation of state model, we can choose any, but I have chosen Walecka model, which is the simplest model that can explain neutron star physics, right, that can describe the thermodynamics of a strongly interacting system. Okay. So, let us start with our thing here, the Walecka model. So, Walecka model is named by after the John Walecka, okay, the scientist, and he developed this model in order to describe the equation of state of strongly interacting physics. So, these are the table of contents of my plot, this PDF, and this is introduction, and what we are going to discuss here is the basic concepts and assumptions of Walecka model, one boson exchange picture, motivation for infinite nuclear matter, nuclear saturation properties, which is very important, Lagrangian density of Walecka model, Euler-Lagrange equation, mean field approximation, statistical mechanics. This seems heavy, but I will walk you through one by one. Okay, so first of all, introduction to Walecka model. See, Walecka model, I told you it is named after Walecka, John Walecka, and it is also known as Quantum Hadrodynamics-I. It's a relativistic mean field model developed by this guy in 1970 to describe properties of nuclear matter and finite nuclei. So, his initial intent was to describe property of nuclear matter and finite nuclei. It was not about neutron star. Later on, we developed it. When I say we, I say scientists, not me. So, quantum hadrodynamics is different from quantum hydrodynamics. So, there is a difference. So, do not confuse it ever. Hydro is something when we are discussing like superfluid, perturbative QCD kind of thing. In heavy ion collision, whenever we are talking in terms of perfect fluid or close to perfect fluid, the models we discuss is molecular dynamics or quantum hydrodynamics, which is different from that. Okay, so this is a phenomenological model. So, when we say phenomenological model, it is based on some phenomena of physics, and it is not a true physics, it is a model, and it is based on what? It is based on quantum field theory, where nucleons interact through the exchange of mesons, right, and it is widely used to model system at high baryon density such as the interior of star. Okay, very far, but not so far. Okay. So, what are the basic concepts and assumptions in this particular model? See, we are familiar with one boson exchange picture, which is also called OBE. So, we are familiar with this Yukawa theory and all those things, and we when we were in BSc or +2 maybe, we know that we used to describe nuclear force as an exchange of pions. So, basically how proton and protons are interacting with each other due to the exchange of pi 0, yes, and when proton to neutron is interacting due to the exchange of pi plus or pi minus, vice versa. So, we understood that at that time the long range part of the nuclear force is modeled by pion, like basically there is a boson, pion is a boson, meson, and whenever there is an exchange between two particles like proton neutron or proton proton or neutron neutron, there is the force is happening, the strong force is interacting, okay, and the meson which is here is pion, is which is basically a pseudoscalar meson. So from the nuclear force we know it has two characters I told you about. So it has the plot, oh not that, okay, it has some nature, like this is a nuclear force versus distance, you know, it is repulsive and it is attractive, okay, and you know it is a long range attractive and it is short range repulsion. So if we want to model this property, this feature in our theory or model, then we have to develop something, we have to use some piece which can describe its short behavior, which can describe its long behavior. The short behavior we have seen that it shows repulsion, and the medium and long range shows attraction. So we can see the short, this one shows repulsion, okay, and this one shows medium range attraction. And since we are describing it in terms of one boson exchange picture, then we assume that there are some particles, okay, there should be some meson which will be responsible for this behavior, okay. And to explain that, we assume that sigma meson scalar, which is a scalar meson, it is a one boson exchange thing, it is a exchange particle between two strongly interacting particle, and it will provide a medium range in attraction, right. So there is one particle sigma which will provide medium range and attraction in our model, and the vector meson, which is again obviously from the name boson, it is a boson and it is a vector meson, and it provides a short range repulsion. So if we have these two mesons, we can model our nuclear strong force. Although the pion is important for low energy nucleon scattering, finite nuclei spin orbit interaction, but Walecka model simplifies the picture by only considering the scalar and vector omega mesons. So we don't have to consider pions in this case because we are not into low energy nucleon scattering, we are more into saturation properties. So we can work without pions. So we can just focus on scalar and vector mesons, okay. So again I will repeat, scalar mesons are responsible for the behavior of strongly interacting physics in the repulsive sector, and sigma is for the medium range attraction sector. So if we have the combination, if we can model our if we can model through these meson, we can create we can recreate the nuclear plot, nuclear force plot, and eventually the equation of state that supports this. Now let me tell you about one more thing here, that what are scalar meson, vector mesons, pions and all those things. So we have to go, I will be traveling back and forth wherever I feel like I have to tell you something, okay. So we know we have a particle zoo, we have leptons and quarks as an elementary particle, right, and then quarks, we have 3 quarks, we are only considering SU3 because SU6 is like with full flavor, but the particles, the 3 quarks like up, down, charm, top, bottom, they are heavy, so they decay immediately, so we are not considering them, okay. So up, down, strange, we are only restricted into SU3, it forms hadrons, hadrons can be divided into baryons and mesons. So mesons can be further divided into pseudoscalars, let me write it here, pseudoscalars, maybe it is better if I write it here so that I can share this thing with you later, okay. Then we have pseudo scalars, then we have scalars, then we have vector, then we have axial vector, okay. So meson can be further divided into 4 group: pseudoscalar, scalar, vector, axial vector. Obviously scalars are the particle which doesn't depends upon like 4 momentum, It depends upon 4 momentum, it does not have the index, and vector mesons are the particle which have the index mu, which runs from 0 to 4, 0 to 3, 0, 1 to 3, right, 4 indices. So, scalar meson is just one. They both are mesons and they both are meson fields. So, they both depends upon x and t. Okay. So, I will also write it as x and t, and I can also write it as x and t. So, this is understood, they are dependent upon space time. Now, what is the difference between pseudoscalar, scalar vector and axial vector? So, when we talk in terms of parity, the scalar has even parity, pseudoscalar has odd parity, vector has odd parity, and axial vector has even parity. So, in terms of parity, we can divide them, and we can also divide them in terms of spin. So, pseudoscalar spin is 0, scalar is 0, vector is obviously 1, axial vector is obviously 1. So, these are the characteristics, these are the properties that make them distinguished, right. So, we are more interested in scalars and vectors here. So, in this particular slide, I only showed pseudoscalars. So, these are only pseudoscalars, right, these three, because pseudoscalars are the particle which we see in nature directly, like they are low energy, they can be easily created like pions, kaons and eta. But when we talk about charmonium and all those stuff with charm mesons, which is also pseudoscalar, okay, it depends upon different things. And vector also, we can see vector easily in the particle collisions, but scalars and axial vectors are hard to find, okay, due to some other reasons. So, we will be talking about scalar and vector mesons, and scalar is even parity, spin 0, vector is odd parity, spin 1. Okay. Now, whenever we talk about these things, we assume that we are in an infinite nuclear matter. What the system we are interested in infinite nuclear matter. It is not a constrained volume. So, we are assuming the volume is enormous. Okay. So, in QCD phase diagram, we consider, like, to study nuclear matter in a simplified but realistic way. So, we have this assumption, we consider an idealized system where the volume is infinite and it is a uniform nuclear matter, it is same everywhere. Okay, it is an assumption, and this removes complication due to surface effect and allow translational invariance. Okay, I will cover that thing when we talk about mean field approximation. Okay, and the thermodynamic limit is well defined, which helps connect microscopic model to bulk observables. Okay, so the thermodynamics is also well defined, which connects microscopic models such as if we take infinite nuclear matter assumption, we can connect our microscopic models like Walecka model to the bulk observable. What are the bulk observables? Like eta, bulk viscosity, all those things, whatever the bulk properties are, bulk viscosities, eta, all those things. So, we can compare our model observable to the bulk observable. So, before going to discuss about mean field approximation, which is related to this line, let us talk about some fundamental things. See, again I will plot my favorite curve. Okay. So, when we talk about this curve, so there is a minima here. So, what is the minima telling us? The minima is telling us a stable position. Okay, it is showing us stability, like the forces are stable now. So, we want our nucleus to be stable, and we know that, like, when we talk about in terms of BSc third nuclear physics, okay, we know that there are different models that try to explain the saturation property of the nucleus. Saturation is like where the forces are saturated, the repulsive and the attractive. Okay, and we try various models to do that. What we do, we try liquid drop model, we try mainly for saturation we do liquid drop model, but to explain some other properties of nuclei, we have shell model, we have vibration model and all those things. So we have already faced that in nuclear physics it is very hard to put one theory together, like just one theory to explain all the properties of nucleus. It is not possible, right? It is not possible. That's why we have different models in nuclear physics, which some of it describe saturation properties, some of it describe the shell level, some of it describe the higher vibrational level. So it has been disintegrated. So same thing goes to particle physics. Like we don't have like single model which can describe the whole QCD phase diagram, but we have enormous model which will describe this. So let us come back to our nuclear saturation property section. So I told you the saturation properties, saturation point is that point where the forces are balanced, repulsive and attractive, and the nucleus is in stable minimal energy. And from the experiment we have understood that the saturation density is around 0.151416 Fermi inverse cube. Okay, you can see my living review in relativity review article. There I have listed all those things. Now, so this is the density, and the corresponding binding energy at saturation is predicted to be around minus 16 MeV from the experiments. It has been observed. So the properties reflect a balance between attractive and repulsive force. This is well observed fact. Now, from that we understood that if I want to create a model, it should reproduce saturation density pretty well. Okay, it should reproduce saturation density around 0.16 Fermi cube. And what else? It should reproduce the binding energy per nucleon at saturation, which is what we observed, minus 16 MeV. Okay. In addition, it should also reproduce some bulk properties of nuclei. What is that? What is that? Compressibility. Okay, so we know that when we have a strongly interacting matter, the matter is incompressible, right? We try to compress it, but it is incompressible. So how far we can go with compression? How do we measure that? It is compressibility modulus. It is denoted by K, and it should be around 250 to 300 mega electron volt. Okay, roughly. I am talking this data from the experiment. And then we have symmetry energy, right? So symmetry energy also tells us about, see, when we have a symmetric nucleus, like for example we have equal number of protons and neutrons, right, then we don't have any correction. But if you go back to semi-empirical mass formula, there were like different terms, surface term, volume term, then we have asymmetry term, pairing term, all those things. So we try to explain the nuclear force curve there. So similarly here, through the model itself we are trying to explain the same curve, but we want to reproduce the main properties, main bulk properties, main saturation properties of the nucleus. Okay, so there we have a term symmetry energy, which tells us that if the protons are more than neutrons, then there is a small correction added to the semi-empirical mass formula. Okay, and for this in our model we can calculate that, and it should be around 28 to 33 MeV. Okay, and then slope parameter is the derivative of symmetry energy, which should be around 88 to 104, maybe 50. So I will just do a rough thing here. Okay, so it is well written in my, again I would say, in my review article. You can visit that anytime if you are interested. So the central idea is, if I want to construct a model, and I started with some mean field model, I chose sigma and omega to be my boson exchange, and I developed a theory on that, and if I want to know that my model is correct and it is correctly calibrated, then I will try to reproduce these properties 1, 2, 3, 4, 5. I will see whether it is reproducing the right saturation density, whether it is reproducing the right binding energy, compressibility, symmetry energy, slope parameter. So it is a challenge, because we have to fit number of observable using different parameters. Okay, so this is one thing. So we have, so far we know about, like for a model like Walecka, we have sigma omega field. Okay, sigma is a scalar meson, omega is a vector meson. Okay, so how do I write the Lagrangian for this, and why do I need Lagrangian? Okay, I don't know whether I should discuss it or not. Okay, for a short recap, Lagrangian is a scalar quantity. It is easier to deal with it. Okay, if we talk about in classical terms, classical mechanics, we usually deal with like kinetic energy, potential energy separately. Then Lagrangian picture came, and we shifted to Lagrangian approach because it is scalar. It is hard to do calculation with vectors, but with scalar it is easier. We get the same result at the end. Okay, and also when we talk about principle of least action and all those things, more general Lagrangian approach is easy. So let us write the Lagrangian of Walecka model. See, before that we have to consider what particles are in our system, right? So what we are actually doing is, we have we have some baryons in the system, which is represented by psi, baryons, antibaryons, and then we have like some sigma particle and some omega particle. Are you with me, guys? I'm just feeling like a little bit disconnected. Can you say, you can see the screen and you can see the math?
Yes, sir.
Yes.
Okay, thank you.
Yes, sir.
Thank you very much. So the Lagrangian density, when I am talking about, we want to create a system mathematically, right? So what particles we have, the first question that comes to our mind is the degrees of freedom we have. What we want to study is a system where we have baryons, let us say nucleons, okay, and then we said, okay, to study these nucleon, I am assuming that scalar meson is the exchange particle which is responsible for the attractive thing, and omega is the particle which is responsible for the, which is the exchange particle which is responsible for the repulsive thing. Okay, so I associated sigma to attractive and associated omega with repulsion. I hope you will be able to read it after that. Okay, and basically what is happening, these psi bar psi is exchanging sigma and omega, hypothetically it is not happening, it is a model. So we are trying to construct something. So whenever there is a short range repulsion, omega, then whenever there is a medium range attraction, sigma. Now the question arises, how to write the Lagrangian? And in order to write the Lagrangian, you should know a bit about quantum field theory. So I will not bore with you all details of quantum field theory. I will just tell you how to write a Lagrangian, and you have to trust me. So let's write the Lagrangian of a baryonic particle. Okay, so whenever there is a fermion, we use Dirac equation to write the Lagrangian. Okay, so this first thing is called Dirac equation for fermion. Obviously Dirac constructed it for fermions. Okay, so this is a Dirac equation of fermion. You can see the psi bar here, it is for fermion, this is psi fermion, and this is the gamma matrices. Okay, and this is the differential, this is a curly derivative, and this is the mass of the nucleon. Okay, so if you want to learn more, you can refer to any book of quantum field theory, like how this Lagrangian is written. For the time being, you just have to assume, you have to just trust me that this is how a Lagrangian is written. So basically what it tells us that how psi bar psi are interacting, and this is a basic idea how do you write a Lagrangian. Okay, so Hamiltonian can be written like, okay, how do I write Hamiltonian? P plus m, right? And if I want to write Lagrangian, it is L P minus m. Okay, and if I want to write Lagrangian in terms of the operator, it will be iota gamma mu p slash is nothing but the time derivative with respect to the space, d by dx mu. Okay, and it should be a psi bar minus m psi. I should have left spaces to put things here. You can see I am not good with making notes. Okay, so what I am doing is here, Lagrangian is, you start with Hamiltonian p plus m, okay, and then you put Lagrangian, which is the p slash operator is nothing but you can write in terms of I eta gamma mu curly upon curly x mu minus m psi. Okay, let's not go there, it will be boring then. So you have to assume that this is the Lagrangian, standard form of the Lagrangian for Dirac equation. Okay, for Dirac equation. Now next, how do I write a Lagrangian for scalar meson? The standard is this. Let me choose a different color. So this is for scalar meson sigma, and this is called Klein-Gordon equation. Okay, so Klein-Gordon equation is the equation which describes the Lagrangian of scalar meson or spin zero particles. So this is the Lagrangian. So it has a kinetic part, it has a potential part. So I missed that. The kinetic part is obviously with the derivative. Okay, and this is the potential part. So Lagrangian has what? The Lagrangian has t minus v, kinetic part, potential part. So we have this kinetic part, potential part, kinetic part, potential part. And similarly, when we talk about omega meson is nothing but vector meson, and when we have a vector meson, we have this Lagrangian minus 1 by 4 to this. Okay, this whole Lagrangian. And since it is a vector field, so we have a definition of this omega mu nu, which is this, and you can see these are the derivatives here. So this is the kinetic energy part and this is the potential part, 1 by half m square v square. You know how to write a potential energy, that gives you the corresponding mass. Okay, so you can relate with the standard classical potential energy with the potential energy of quantum field theory way. So this was what, Proca, not Proca, this is not Proca, but I would say this is a vector Lagrangian. Now if we have photon, okay, for photon case, what will happen? Photon is what, vector or scalar? Anybody? What is the spin of photon? Okay, photon has a spin 1 and it has a non-zero spin. Okay, that's why it is vector. And how do I write the photon Lagrangian? I write it like this, plus half m square omega m square photon, let us say gamma, and then we have photon field. But since photon field something right here, but photon doesn't have mass, so there is no second term. So only term which the Lagrangian of photon is only this, which is also called Lagrangian of electromagnetic, and f mu nu is what, electromagnetic tensor, which is similar to this when we replace the corresponding field. Okay, so far we understood three terms, this and this. Okay, what about these guys here? These are called interaction terms. So you can easily anticipate here, this is interacting with itself, the baryon is interacting with itself, here the sigma is interacting with itself, omega is interacting with itself. See, so there is no cross interaction between baryons with sigma or baryons with gamma. So how do we do that? We have this interaction term psi bar sigma psi, and we have this interaction term psi bar gamma mu omega mu psi, okay, which tells us, okay, the Lagrangian tells us the interaction between baryons and omega. baryons and scalar, which is very much needed. Like how else you would know like how baryon is interacting with scalar meson? That is the central idea of our model, right? And whenever there is an interaction, there is a coupling constant which decides the strength of that particular interaction, and the coupling constant is this guy, okay, G sigma or G omega. So G sigma G omega coupling constant. Okay, so these are very important parameters. So by changing the parameters, you can change the strength of this particular interaction. So this is, so far we learnt about the different parts of the Lagrangian, the interaction within themselves, the particles, then the cross interaction between baryons and scalar mesons, baryons and omega mesons. Now the second question that could arise in your mind, why there is no interaction between sigma omega? There should be some term sigma, G sigma omega something with all this vector thing. But because there is no need, sigma and omega are the virtual particle which we have decided to put in our model in order to describe some physics. We don't care about how they interact. There is no need. Okay, so far we understood psi is the nucleon Dirac field, sigma is scalar meson field, omega mu is vector meson field, omega mu is the derivative, the tensor, and G sigma G omega is the coupling constant. And last but not the least, it is very simple, Mn is the mass of nucleon, and sigma is the mass of sigma particle, m omega is mass of the omega meson. Okay, and these are input, we can put that, we know that, we calculate that, but we know that. Okay, now so far so good with Lagrangian, like how we construct it. If you want to know more, you can,
Yes.
yeah, you can refer to your quantum field theory books, then you can have better idea. So right now I am just giving you the motivation. Now we have the Lagrangian. The Lagrangian tells us about like physics in mathematics, like how the particles are interacting, how the fields are gonna interact with each other. So when we are ready with the Lagrangian, the next step is to get real physics out of it. What is that? We need to know how the particle, they are interacting with each other. We need to think how they are evolving with space time. This is the central idea of physics, right? We want to see the change, and from that change, from that mechanics, from that kinetics, we want to know what happened. And to do that, we need to get the equation of motion. How do we do that? How do we calculate the equation of motion from Lagrangian? So we do by applying Euler-Lagrange equation of motion. Okay, you must have done like various calculation if you are have already done MSc physics in the first semester classical mechanics. This is the thing we learned. Okay, if you have not, you have to trust me. So we start with Lagrangian. We started with the Euler-Lagrange equation of motion for a particular field. You can replace this field by your particle. Okay, so we have Euler-Lagrange equation of motion, and when we put that Lagrangian in this equation of motion and we solve it, we get something, right? So we solve it for 3 systems, 1, 2, 3. So we solve it for 3 systems one by one, and we get 3 results. Obviously we get 3 equation of motion, and we get so I am not going to do derivations here, that would take a lot of time, but I can provide you the solution if you need, or I would like you to do it because you will learn something. Anyhow, so we put Lagrangian here and we get this equation number 4 when we solve it, okay, the derivatives and everything, and we get to know that okay, the new form of the Lagrangian is something like that, not the Lagrangian but equation of motion. And scalar, for scalar meson field, when we did that for sigma, we get something like this, and for vector meson field we get something like this. So we get to know that in the nucleon field equation there is an equation that is pure in fermion, like psi here, and then there is some interaction between sigma and psi, and then there is some interaction between omega and psi, and we have the coupling parameters, which is very important, right. Similarly, we learn to know that the sigma interacts with itself and it interacts with the baryons or fermions or nucleons, and then similarly we got to know that it interacts with itself and then interacts with the particles. Now, so these are the three equations of motion. Now, when we have the three equations of motion, the next step that comes into mind is how can I solve this three equation of motion, and these three are differential equations, right. Let me show what I have in my next slide. Okay, so these three are differential equations and I want to solve it, and you know it is difficult to solve a differential equation when they are coupled. Why I am saying coupled? Because psi is here, psi is here, psi is here. Okay, psi bar is here, psi bar is here. This is the simplest example. There could be sigma is here, sigma is also here, or omega is here, omega is here, something like that. But right now it is coupled with psi, coupled in psi. So this is a system of equation which should be solved simultaneously. That is a one hardship for that, and the second layer of the problem is the differential equation that we have to solve, du mu. So what is d mu? Basically it is dx mu. Okay, this is the derivative. Let us say d0, which is dx0, this is dt. Okay, if we talk about d1 or dx, this is simply dx1 or d by dx. Okay, so we need to put some we need to solve this equation, which is tough, but then mean field approximation comes into picture. Again, you know, it is very difficult to solve a system of equation. This is challenging. Your computer will give up when it tries to do that. Why? See, what is happening here, let us say I have a box and I have so many particles in it, and it has an infinite nuclear matter. Come on, it is a complex system. I don't know how many particles in it, and they are interacting with each other, with the nearest neighbor. Okay, they are interacting heavily. So every particle has, let us say particle is p, it has some space time dependence and it is interacting with each other, and it is making the system very complex, It is very hard to do some calculations like that. So in that case we have to assume a mean field approximation, which I will explain why the name is mean field approximation. And when we assume that for infinite nuclear matter, when the matter is infinite, there is no boundary, and the matter is uniform, then meson fields are replaced by their expectation values, and only time-like component of omega mu survives. Okay, I will explain that here. See, previously my meson depends upon x and t, omega mu depends upon x and t. Okay, and I have a lattice where the particles are located like fermions, psi bar psi. Let us say psi only. Okay, so they are there. Now they are interacting with each other, you know, there are psi everywhere, proton, you can say. Now if there is no mean field, the matter is like in a perturbation everywhere. We have a different value of some force. Come on, we have different value of some force. The interaction that the particle is feeling is different at different x and t. It is very hard for us to model this kind of system because it is highly dependent upon the derivative, you can see. And if we have so many variables, like it depends upon x and t everywhere, the system will be very hard to solve. So we need to get out of it, we need to get have some assumption in order to get rid of this. So what we do, we assume that in infinite nuclear matter, meson fields are replaced by their expectation value. Like we do an average. So we do this. So what I want to say is here, so instead of sigma having x and t everywhere dependence, here it is changing, I assume that sigma doesn't change. Sigma is for a particular temperature and for a particular density, it doesn't change, it is always sigma, it doesn't depend upon x and t. Okay. So in that case, I reduced one complexity layer in my system, that my sigma is everywhere same, and I can solve my equations easily. Okay. So it is in a mean field. Now the field is mean, it is not mean like the English mean, but it is like mean, average. Similarly, omega mu, omega mu also depend upon xt. I want my omega to be same everywhere, so I put this relaxation. Okay, in the mean field omega is same. Okay, I layer down one more complexity, and I put my sigma to sigma, xt to sigma, omega mu xt to omega mu, which becomes eventually omega 0, because if it sigma is same everywhere or omega is same everywhere, then there is no translational variance. The translation, it is translationally invariant because it doesn't depend upon t, not depend upon t, but depend upon x. Okay, it doesn't depend upon x. If the sigma is same, omega is same everywhere, it is what? Translationally, where was that thing? It has allows translational invariance, and it also removes complications due to surface effects. What does that mean? See, if the particles are not confined, the volume is infinite, it is an infinite nuclear matter, then it doesn't matter whether the surface effect of this particle and this particle, whether they are in the picture or not, because they are not very close, they are very far, they don't care about this thing. Okay. So this was the thing about mean field approximation that we do to layer down the complexity of the system. Now again, if there is no space dependence, then there is no point to take the derivative like with respect to space. So d by dx with space will be 0. Okay, so that layers down the complexity of the system. Okay, and it only reduces it from like there are 4 indices. This is a 4 momentum notation, and same for the derivative. If we are only talking in terms of d0, then this is just d by dt, and it also depends upon what signature you are taking, but right now I am just gonna skip that. So our system reduces to only temporal thing, and it doesn't have any spatial dependence, so we are more easy with these guys here. Okay, derivatives. Now when we put the derivatives like in a simplified version, and we replaced our sigmas with average value and omega with average value, and we solve this equation like one by one, we get something like this. For sigma we get something like this, for omega we get something like this. Okay, you have to trust me, I will share you the derivation if you want. Okay, so this equation reduces to this. Now we have these 3 equations, but after the omega mean field approximation, that reduces to, for sigma and omega, that reduces to only these 2 equations. So we have these 2 equations and one equation with the Dirac. One equation is with the nucleon field. One more thing I would like to tell is, like, we can extract effective mass from here. See, the standard form of Lagrangian is, the equation of motion is I gamma mu curly mu minus mn psi. This is the standard form of Lagrangian, but we by using the interaction for sigma and omega, we get to know that there is something additional going on here. If there is something additional going on, that should be encapsulated in something else. So this is not a scalar thing, it cannot go into mass, but these guy can go into mass. So I can rewrite my equation this like I gamma mu gamma girly mu minus mn minus g sigma sigma minus g, I would say some function of omega, and I will make there is no need to close the bracket. Okay, so I get this equation. I can further write it like I gamma mu curly mu, and I will write it as m star n minus some function of omega. So what I learned from this is I can rewrite my this thing as m star n, and later on I recognize this m star n is nothing but the effective mass. So what is an effective mass? It is the mass that has been changed by the interaction, that's why it is effective. And mn is what? Vacuum mass. What else? M star is effective mass, and this psi dagger psi, which has been replaced by rho b, is called baryon density. Okay, it is a number density, also called number density or vector density, fancy names. Then we have rho as psi bar psi, which is a scalar density. Okay, so so far we got to know that we had three equations, and for each of the equation we reduced it to a simplified equation with the help of mean field approximation, right? This. So now we have three equations which are simplified. One equation is this guy here, I will put that into the document here somewhere, and then we have sigma, then we have omega. So this is less complex equation. Now I want to solve it simultaneously. Okay, this is a challenge where the coding will help. Okay, then we have some statistical mechanics thing, I can just skip it for the moment. What I want to tell you is like since we have these equations, okay, let's stop here for a moment. So we have three system of equation, one for fermion, sigma and omega. We can solve them simultaneously because psi bar is a common thing, like we have to solve it for density, and we get a solution of sigma and sigma omega out of it. So when we get a solution of sigma and omega out of it, we can put it back in the system itself and we can calculate some properties. So from thermodynamics itself, we can calculate the energy density expression and pressure for the same. Okay, so the pressure can be calculated through the Lagrangian, and it can be calculated from the grand canonical potential as well. So I don't want to overwhelm with you, overwhelm with all these things. Okay, so the energy density is this, you have to trust me, the expression for energy density looks something like this, and the pressure looks something like this, and these calculations are at t is equal to 0. Okay, and you know the distribution function behaves how at t is equal to 0, it is a step function. Okay, so it has a Fermi sphere which goes from 0 to the maximum momentum, which is kf, which is the Fermi level. You know that at t is equal to 0, all the states up to Fermi levels are filled, right? So we will only integrate from 0 to the maximum Fermi level, and then we have this integral, then we have this expression for sigma, this expression for omega, and which is energy density, and same for pressure. Now what I want to tell you is, if I have m star, I have sigma and omega value, these are inputs, I can calculate my pressure and energy density. Okay, similarly, how do I get sigma omega? We can solve this equation of state simultaneously, which is the next task for our next class. Okay, how many pages I have? Okay, I'm just gonna finish it. So the main part we already discussed, the extensive part when we needed a lot of discussion. So at the end, what we wanted to calculate is, we wanted to calculate the pressure and energy density. Okay, which is given by this, and when we have sigma and omega from the code itself, we can calculate these quantities. We can put them into some output file. You guys are familiar with pandas now, we can do that, and we can extract that equation of state to the TOV solver. Okay, that is our next task. What are the merits and demerits of Walecka model? So merits are relative, it has a relativistic treatment. You know, when we are describing a strongly interacting matter, then we should use a relativistic model, because the strongly interacting system, when we describe in terms of quantum field theory, there are relativistic particles. So though our model should be relativistic. One thing, merit, it reproduces the saturation property and compressibility of nuclear matter, very good, and it can be, this is at T is equal to 0, and it can be straightforward extension to finite temperature and beta equilibrator matter for neutron stars. So it is very important, guys. So the matter so far I have talked about is not ready for neutron stars, because it is not charge neutral, it has some finite charge fraction. But when we talk about neutron stars are neutral. The matter should be beta equilibrated and charge neutral. I will talk about this more in our next lecture, about all this beta equilibration and charge neutrality, right? So it can be done in Walecka model. And demerits, it overestimate compression modulus. Like I told you, it should be around 200 to 300 MeV, but it overestimate by 500 MeV, and it has much higher, like the result is much higher than the empirical value which I suggested. So it doesn't have pions or isospin dependent terms, it has a poor description of matter. So what does it mean is that it only works for symmetric matter. What does symmetric matter mean? Where number of proton is equal to number of neutrons. But in ideal case, this is not necessary. We have like significant amount of matter in the universe which is asymmetric. For example, lead is asymmetric, gold is asymmetric, where number of proton is greater than number of neutron. So what we are so far we have learned, we have only described the symmetric nuclear matter where proton number is same as neutron number, but this is not good to describe heavy ion collision matter, because in heavy ion collision matter, heavy ions are itself asymmetric, right? So this is a one major drawback. So we can make it work, we can add some equations, we can add one more exchange particle that accounts for asymmetry, right? That is doable. Needs nonlinear extension to model finite nuclear property. Okay, it needs some nonlinear extension. I will not go there. So let's leave about that. So extension to the Walecka model. What can we do? So we can add nonlinear interactions. You know, I hope you are familiar with this thing. Whenever we want to add fluctuation to our system, like perturbation to our system, we expand our series. So initially we drop some items at the higher level. Okay, let's not focus about next to next leading order or next leading order. We can drop some linear self interaction terms, non-linear self interaction term. But if we want to improve our physics in the model, we want to see something which might be useful, we always go with that discarded term, truncated terms. So we add that into our system and we try to understand something. Okay, if you are familiar with perturbation, you can relate more. And then we can include additional mesons. I was telling you, if you want to include isospin. Isospin is related to asymmetric matter. If I want my number of neutron to number of proton, number of neutron should be greater than number of proton, that is a asymmetric matter. How can I add that? If I add an additional delta meson, like a mean field. Coupling mesons to density dependent function, we can do that, or we can also incorporate chiral mean field model, like some advanced model like chiral mean field, or like some advanced parameterization, or some advanced model that can model these things very well, that can reproduce the nuclear saturation properties very well, and that can also reproduce the lattice constraint or perturbative QCD constraint very well. Okay. So, in conclusion, the Walecka model provides a foundational framework for understanding the thermodynamics and microphysics of nuclear matter in a relativistic context. Its strengths lie in simplicity and predictive power for symmetric nuclear matter, making it an excellent starting point for more refined model. So, this model is a starting point because it does not describe the ideal nuclear system, right? No model can do that, but it is a very simplistic model that can start us with understanding thing, right? So, we learned how to calculate the pressure or energy density of a nuclear matter. Okay. So, when we will be doing like real thing like computational physics, then you will get to know about all the details, like step by step you will understand what is happening. Okay. So far this was the theory side, and I don't want to overwhelm with you CMF. By the way, CMF is the model which I work. I don't work in Walecka model. So CMF is bit advanced, very heavy model. So we can write Walecka model in maybe 200 lines or maybe 300 lines, but CMF the code I have is maybe 6,000 lines in Fortran, and more than that. So it is a bit complex code. Then we have conclusion and preparing for the code. Now what I'm just gonna be done in 5 minutes or 10 minutes max. You just have to bear with me for a couple of minutes. See, now we know the problem. We started with Walecka model Lagrangian. We derived the equation of motion for sigma omega fields. Okay. We calculated energy density and pressure for a given momentum, and we gradually move to model with non-linear terms and additional mesons. We will do that if needed, but we definitely add beta equilibrated and charge neutrality in order to develop an equation of state for neutron stars. We will do that next time. Now, what are the suggested steps for implementation? Okay. So, what we have to do, we have to identify what are the inputs and outputs in our code. We have to define the physical constant and parameters. We have to loop over baryon density or chemical potential. What we want to do is we want to get something like pressure versus chemical potential or pressure versus baryonic density, right? So, we have to loop over baryonic density and corresponding pressure we have to achieve. Now, we saw that these are self consistent equations, right? These are sigma, omega, psi bar psi, and we have Dirac equation. So, we need to solve them simultaneously. So, to solve them simultaneously, we need to know a method like some computational numerical method which can do that. We can start with some method. I will use a default fsolve method of Python to solve such system. Fsolve method to solve non-linear equations. Okay, let me write. I will update this PDF and send it to you. Then at last we will plot the equation of state like P versus energy density, effective mass versus baryonic density, field values like sigma versus NB or sigma versus omega versus NB. So, we will get to know about that. Okay. And if you want to know more about Walecka model, you are encouraged to solve the following derivations. Okay. So, this is the Lagrangian of Walecka model. So, for only scalar meson you can try deriving the equation of motion. Similarly, for vector field you can try deriving the equation of motion, and you can derive the scalar and baryon vector density. You can also check this. So, these are some optional exercises if you want to learn more, and if you want to do, let me know. I will be happy to help, but I will have to make some notes. So, just let me know. So, I guess this was about my lecture today. Let me get back to my screen here. Okay. I am back to my computer. Okay, so this was so far the hardcore physics thing. I hope you liked it, and if you have some questions, this is the time to ask.
Sir, have you uploaded that in a drive also, review?
What thing? The current PDF I was showing?
Yeah, that research paper.
No, I may not. I will upload the written thing, right? And I also got to know that I have to improve some some text. So I will do that today later, but I will deploy it right now, the current version I have. Okay, any other question? Okay, you guys do not have any question, then let me just say something and we will hang up the session. See, these things are new to you. I am not sure how many of you are familiar with all these things. This would be too much for you, maybe not. So if you feel like you didn't get anything, you can always watch the video again and again, and I always try to give you a simplistic approach so that you can understand more, right? And if you are interested in particle physics, I will definitely recommend you to go to that Dr. Physics video, so that you have an initial motivation about all those strong interaction physics, field theory concepts. And if you want to do advanced learning, you can read some mathematics, but you will do it eventually in MSc or PhD courses, right? And yeah, just the last question, did you find the pace well for the physics, or I was fast, I was slow? I think I was fast, or is it fine? Okay, it is fine. Okay, then let's meet on June 20. On June 20 we are gonna discuss again. I will revisit some of my notes for beta equilibrated matter and charge neutrality. I will try to explain that thing, and eventually we will start writing the code all together that day. So be ready, and assignment 2 is already deployed. Go through that, give your maximum hours in that, and from your output I will be able to understand that you are really learning something in this internship, right? So it is going to be very hard now, because you have to deal with all this assignment 2 as well as these physics problem. So bear with me, I am here. I will be happy to help anytime you need. So with that, I'm gonna say bye to all of you. See you next time.